Welcome to the Turf Zone podcast. This episode features the article, Plant Growth Regulators and Biostimulants for Fine Turf. What's the difference? Written by Richard E. Schmidt, Professor Emeritus, Virginia Tech. Read from the July/August 2026 issue of Virginia Turfgrass Journal. Introduction written by Mike Goatley, Jr., Professor and Extension Turfgrass Specialist, Virginia Tech. Virginia Tech Professor Emeritus Richard E. Schmidt passed on December 31, 2025 at the age of 94. Upon the passing of his wife, June, in 2022, Dick's son, Stephen, asked me to please keep Dad active and engaged by involving him in a project. Well, the project I asked Dick to work on for me was to summarize what he considered to be some of the most significant findings of his research of biostimulants as compared to more traditional plant growth regulators. Dick literally continued to review articles and write from that point until he was prepared to pass, calling me on December 30th to let me know that he did not have much more time and it was up to me to complete this article. There was little that was needed for me to complete this article, but it was my pleasure to provide the final review and edits to Dick's last scientific publication for the turfgrass industry. I decided I can't give you everything Dick was exploring. He went into areas of literature review on gene regulation and expression in plant hormone production, the chemistry and production of phytosideraphores, and a host of other topics that I simply am not qualified to discuss. My effort focused on refining Dick's article in a way that I felt would most benefit you, the turfgrass manager. Dick is referred to by many as the godfather of turfgrass biostimulants, but his recognition for his efforts in better understanding these compounds did not come without professional challenges. He was often confronted by scientific peers that he should not be wasting his time doing snake oil research. But Dick remained resolute that these compounds had the potential to play important roles in managed turfgrass, especially turfgrass that was likely to encounter environmental stress. Dick, along with research scientists like VT's Dr. Zhenzhong Zhang and a number of graduate students such as myself studying under him at Tech, slowly but surely progressed in the understanding of why and how these compounds might work or not, rather than just practicing the approach of spray and pray. VT Turfgrass alum and Purdue University Turfgrass Professor Dr. Cal Bigelow made a comment about Dick's legacy that I thought was very astute. I dare say that almost every high-profile golf course or sports field anywhere in the country likely has some formulation of a biostimulant in their chemical room that the manager is applying as a standard tool in their management program. I hope you will take a few minutes to read Dick's final article on this subject matter as a way to pay tribute to his lifetime of research efforts and to learn a little more about how to use these compounds to improve your turfgrass management program. Plant growth regulators and biostimulants for fine turf. What's the difference? Are you confused concerning the use of plant growth regulators, PGRs, or biostimulants? First, a couple of basic definitions of these compounds to set the stage for this discussion. For the purpose of this paper, I will define a PGR as any compound that alters plant growth or development, and a biostimulant as an organic substance derived from plants and animals that, when applied in small quantities, may enhance plant growth and metabolism to enhance turfgrass tolerance to environmental stress. There is definitely some overlap in these definitions, so it's understandable if you are confused by the distinctions between these two classes of chemistry. Conflicting information concerning the efficacy of newly introduced materials occurs frequently. Dr. Bill Cruiser, 2015, points out the advantages of using plant growth regulators for fine turf. Subsequently, VT alum Dr. Jordan Booth, 2023, advocates managing bentgrass putting greens in the transition zone without plant growth regulators. Here are two highly regarded scientists with quite variable viewpoints on this subject, and I think both are correct in their findings and recommendations, depending on the situation. To get a perspective on the subject, let us briefly review the history of the use of compounds that fall outside the category of fertilizers but are known to affect the growth and development of plants. Prior to World War II, a growth hormone in the form of the herbicide 2,4-D was introduced to selectively control broadleaf weeds in turfgrass populations. Reports of effectiveness varied. Its application for weed control did not become widespread until sufficient research was conducted to show that applications made during the winter months were not effective until warmer weather in the spring, when broadleaf weeds were actively growing. Once it was established that this chemical effectiveness was influenced by the environment, its use became standard. This is a reminder that from the beginning of the use of synthetic chemicals, that environmental condition must be considered in obtaining desired results when applying chemicals to turf. 2,4-D and similar compounds later became standard components in tissue culture research in the selection and development of new turfgrass cultivars through callus culture. This positive growth response of 2,4-D clarifies something that we have long known for pesticides, hormones, fertilizers, etc. Concentration is very important. In search of compounds for faster growth responses. Other factors and compounds must also be considered when discussing the initial research into the possible use of these compounds. During the 1980s, the first synthetic gibberellic acid (GA) compounds became available. Research by Dr. Felix Juska, 1958, detailed how gibberellic acid stimulates plant growth by elongation of stems between the nodes. This was originally thought to be a miracle compound for turfgrass culture. However, by the late 1980s, use of GA as a plant growth accelerator was basically terminated except for specialty uses such as pre-germinating perennial ryegrass seed for sports field surface recovery uses, a standard practice by many sports field managers still today. When delving into the reasons cited by scientists and turfgrass managers alike why GA use essentially ceased outside of seed treatments, it seemed that the general consensus was that once a dense turf was established, most managers desired that the grass grew more slowly to decrease maintenance cost. Perhaps compounds for slower growth? To obtain slower turf growth, there was also a lot of interest in the 1980s in the development and testing of plant growth regulators (PGRs) as a component of turfgrass management, with initial compounds mostly being used on unimproved turf for radical reductions in foliar growth or seedhead development. Emphasis for fine turf management was placed on synthetic gibberellic inhibitors, such as compounds still widely used today in paclobutrazol and trinexapac ethyl, to control foliar growth of turf grasses and improve turfgrass density and playability. One common theme with their use that was first somewhat surprising to end users was the surge of foliar growth when the regulated turf was removed from the treatment program, a phenomenon often referred to as the rebound stage of growth and development. Clipping yields increased drastically during the rebound stage due to a buildup of carbohydrates and stored nitrogen in the plants that accumulated during the suppression phase. This is further evidence of response that is due to concentrations of hormones inside the plants, as well as the interactions with other compounds. I briefly mentioned before how 2,4-D is most commonly thought of as a broadleaf herbicide, but at low concentrations it can trigger very positive auxin hormone-based responses that promote cell elongation. The late biochemical pathway suppression of GA by a class, a PGR like trinexapac ethyl, revolutionized how fine turf is managed with a PGR. The main beneficial claim for using gibberellic inhibitors is the reduction of clipping yield plus the enhancement of color, increased stress tolerance, and reduced nutrient requirements. Because of the short growth suppression phase, frequent retreatments are required. It is impractical to visually determine the effectiveness of the gibberellic inhibitor treatment to ascertain when retreatment is necessary. One standard method in golf turf putting green management has been golf ball roll distance, when ball roll is slowed because of faster turfgrass growth rate, as measured by an increase in clipping yield. It is a signal to retreat. Technology and smart devices have now made it common to have PGR treatment prediction models that combine data collected over the years with varying rates and sources of PGRs with growing degree day data. This is an example of how technology is helping the turfgrass manager further refine their PGR management programs and maintain consistent ball roll speeds for their golfing public. Growth inhibitors or metabolic stimulators. Although classified as a PGR, naturally occurring growth regulators such as seaweed extracts and humic acid are not discussed in the same ways as gibberellic acid inhibitors. This is because the main effect of the natural growth regulators is in metabolic enhancement, and these compounds are commonly referred to as biostimulants. By this definition, some PGRs also may be classified as biostimulants, as they also influence the metabolic activity of plants. Therefore, when a material is used to influence plant growth, it often is being used primarily as a PGR. When it is used to affect the metabolism of the plant, it may be referred to as a biostimulant. It has been well documented that turf grasses under environmental stress have an internal increase at the molecular level in potentially phytotoxic oxygen species called free radicals within their cells. Simply put, the plant is incapable of utilizing all of the energy from the sun that it is receiving, something we generally associate with photosynthesis and think of as a good thing, because it is leading to food production. Under conditions of excessive energy absorption, oxygen molecules accept electrons and become a highly reactive free radical form. These free radicals are capable of damaging cell membranes. Under normal conditions, the plant has biochemical pathways in place to neutralize free radical formation, but under stress, the buildup of free radicals exceeds the plant's capability of quenching that excessive energy by the production of compounds called antioxidants. It has been shown that supplemental applications of biostimulants, particularly before the most extreme periods of stress arrive, can enhance the development of the antioxidant compounds that can mitigate the toxic influence of the free radicals. Whether materials are applied for growth control or development of antioxidants, environmental conditions must be considered. For example, research has shown that adequate nitrogen fertilizers in the fall and early winter, when grass foliar growth is reduced by cooling temperatures, carbohydrate reserves increase, and this ultimately favors root production. However, heavy spring nitrogen fertilization stimulates foliar growth at the expense of root production and places the plant under stress, particularly if the summer months prove to be hot and dry. In Booth's 2023 article, he makes the case that applying PGRs, such as those that inhibit gibberellin production, can add to the stress associated with the summer weather. Data, however, shows these products do influence the metabolic processes that are reported to negate the effects of environmental stress. Other interacting factors that influence the action of the biostimulant are nutrient balance and slash or pest activity that negates the results of the treatment. It is difficult to visually observe changes associated with PGRs, and the opportunity to adjust programs is often missed. Again, one of the best but time-consuming strategies to adjust programs is to take daily stimpmeter readings to assess ball roll and slash or clipping yields to determine the level of plant growth effect of the supplemental PGR treatments. Relation between metabolism and plant growth responses. As a means to hopefully better explain some of my earliest research findings in terms of PGR/biostimulant concentrations and turfgrass responses, and what I have found in my literature review beyond my time as an active faculty member at Virginia Tech, I turn to findings from a scientific publication from the work done by my successor in turfgrass physiology research at Virginia Tech, Dr. Eric Irvin. Irvin et al. 2004 published a paper on the seasonal influence of biostimulants on root growth, metabolic activity, and overall shade tolerance of creeping bentgrass, an article that covers both basic and applied research findings in this area. Root development of bentgrass, as measured by physical root pools of plugs grown under the first shade treatment sequence of 88% shade from June to the 30th of October 2001, summer through early fall, was not enhanced by trinexapac ethyl, iron, or seaweed plus iron treatments, but had an approximate 44% increase for treatment with a standard fungicide, propiconazole. When returned to light conditions for the next 6 months, November to April 2002, late fall through winter, all root pool measurements were much greater than before, with increases of 37, 41, 20, and 17% respectively for trinexapac ethyl, propiconazole, iron, and seaweed plus iron treatments, compared to the untreated control. When shade was introduced again from April to November 2002, spring to fall sequence, root strength once again declined due to the shade, but trinexapic ethyl propiconazole, the active ingredient in a standard fungicide shown to have hormonal-type activity in previous VT research, iron, and seaweed plus iron treatments all provided root strength increases of 92, 33, 24, and 6%, respectively, as compared to the untreated control. Two factors are at play here. Root development is obviously linked to the plants producing energy in the lighted conditions. Secondly, grass roots tend to develop during the late fall/winter months when foliar growth was impeded. The bent grass receiving the trinexapac ethyl treatments retained the most root development compared to the control when measured in November 2002. This indicates that the benefits of treatment that enhanced root development during the winter period when the bent grass was exposed to light persisted. Although the treatments that had the largest root development, bent grass treated with trinexapac ethyl under full light in the winter, October 2001 to April 2002, because of the root growth response, they also had the largest percentage root loss the following spring and summer when grown under shade. However, in terms of absolute root numbers as determined by root strength measurements, the bent grass receiving these treatments still had significantly better root growth than the untreated control. Metabolic activity. Now, how about metabolic activity? Two metabolic variables measured in this shade trial were photochemical efficiency, PE, a measurement of how efficiently plants are utilizing photosynthetically active radiation, and antioxidant activity, a measurement of how the plants were capable of quenching the potentially membrane-damaging energy of free radicals by way of an increase in an energy-quenching compound, superoxide dismutase. PE levels under shaded conditions increased slightly for all treatments compared to the untreated control, but the values only range from a 2% increase for seaweed extract plus humic acid to a 9% increase for trinexapac ethyl. While the dense shade drastically reduced all levels of SOD in shaded plants, the relative increases in SOD in the treated bent grass compared to the untreated control was 39, 74, 78, and 86% greater for seaweed extract plus humic acid, trinexapac ethyl, propiconazole, and FeSO4, respectively. Greater SOD levels in the plant impart improved stress tolerance to the bent grass as it was moved from the shade to sunny conditions. Now, clearly the treatments were no replacement for growing grass in sufficient sunlight, correct? But under such extreme light deprivation, the treatments did trigger the plant's metabolic responses to improve shade tolerance. What this might mean for future objective assessments of overall turfgrass health. When combining the metabolic enhancement data from the bent grass shade investigation trial with that of the root development under altering shade and light conditions, it is evident that in general there were positive responses to the PGR and biostimulant treatments. Determination of the antioxidant activity to ascertain turf health in real time is a wet laboratory process and would be impractical for the average turfgrass manager to use it to measure health of the grass. However, the remote sensing technologies that the research teams of Drs. McCall and Askew at Virginia Tech and scientists at other universities are evaluating, coupled with the expanding availability of these types of tools to golf course superintendents and sports field managers, and a summary/evaluation of computations possible through artificial intelligence, I think it is likely that one day soon the turf manager will be determining the PE and SOD levels, etc., to assess turfgrass health both rapidly and accurately. While ball roll speed, trueness of roll, and slasher clipping yields will always give the turf manager very meaningful data in terms of management decisions that affect health and playability aspects, the use of electronic tools will provide the turfgrass manager real-time data to tweak the metabolic activity of the turfgrass by way of a PGR or biostimulant application. Summary. Although turfgrass ecology is a science, it also very much remains an art as well. Therefore, we should always respect the observations of dedicated turfgrass professionals that pay such close attention to their grasses on a daily basis. Their judgments and measurements reflect the ideal and the extremes in environmental conditions, and their exploration with the pros and cons of PGRs and biostimulants have demonstrated the possibilities and pratfalls for how these tools can affect metabolic processes within the plant that may or may not promote better stress tolerance. For as much progress that has been made in this area from the time I began studying biostimulants in the 1980s, there is no doubt that there is so much more we don't know. There are an infinite number of plant hormone concentration possibilities inside plants that trigger plant responses, and with the application of the biostimulant, the turfgrass manager is trying to effectively and safely manipulate that hormonal balance. Add to the equation the diversity of turfgrass species, climate, soils, pests, maintenance protocol, turfgrass use, etc., and you can appreciate the challenges involved in gaining the desired plant responses. I have somewhat alluded to it, but I don't think I have completely addressed this point. When Dr. Goatley first spoke with me about developing an article about biostimulants and PGRs, he made the statement that, in particular, one needs to know exactly what is in their biostimulant package if they are on a PGR program. I agree, and it's a reminder that carefully reading and following the label is no different than for a pesticide. For instance, if a turfgrass manager is on a trinexapac ethyl regulation program and is simultaneously applying a biostimulant that contains GA, their growth regulation is very likely being affected since they are applying the antidote to the PGR activity. There always will be research that needs to be conducted in this area, and I am pleased that the lab of Dr. Zunjiang Zhang at Virginia Tech continues to expand knowledge in this area. Dr. Zhang has published research showing that turfgrass stresses such as drought, salinity, temperature, exposure to UV light, and shade can be reduced by elevating plant antioxidant levels by way of biostimulant applications. Biostimulants are not and will never be replacements for sound management strategies, but they are tools that, when applied at the right time and concentration, can enhance stress tolerance and improve the health and performance of your turfgrass system. You have been listening to the Turf Zone podcast. Follow the Turf Zone on X, Facebook, and LinkedIn for all things turfgrass, featuring podcasts, magazines, events, and more.